Todavía no empezamos, ¿no? A grabar. Ok. So, welcome to the global, no, to the non-commutative geometry seminar. Our speaker today is Rubén Martos Prieto from the University of Copenhagen, and his talk is the title there, Projective Representations for Compact Quantum Groups. Please, Rubén, go ahead.
Thank you. Thank you for the presentation. And first of all, I would like to thank all the organizers of this seminar. I guess that you are hear me well. So yeah, thank you for the organizers for the invitation. I'm very glad to give this talk here. So yeah, the title is this projective representation theory for compact quantum groups. So more precisely, I will talk about recent work in collaboration with Kenny DeComer and Richard Nest about this theory for compact quantum groups and some applications in the context of the Baum-Connes conjecture for quantum groups. So first of all, let me give a very brief introduction about quantum groups, just basically to fix the notations that I will follow in the talk. So we are going to work in the context of compact quantum groups in the sense of Voronowicz, which means so such a quantum group will be denoted by a letter double G like this, and it will be defined in terms of a unital sister algebra that I will denote by C of G, and the co-multiplication delta. And at some point also we'll need the von Neumann algebraic version of a compact quantum group, which will be given by the same data, but instead of a sister algebra, we'll consider a von Neumann algebra, which will be denoted by L infinity of G. Also, for the rest of the talk, we'll make the standard assumptions that G will be reduced, which means that the Haar state is faithful. Okay, so for those who maybe are not familiar with quantum groups, we can just think about quantum groups defined in terms of classical groups. So for instance, if G is a classical compact group, then by considering the continuous functions on G with the co-multiplication defined in terms of the multiplication on G, this data will define a compact quantum group in the sense of Voronowicz. And also given a classical discrete group gamma, then the reduced sister algebra of gamma with the co-multiplication given by the group-like co-multiplication will define also a compact quantum group, which will be denoted by this double gamma letter here. In the theory of Voronowicz, there is also a nice duality in the sense of Pontiac-Green duality. So given a compact quantum group, we get a dual, a Pontiac-Green dual, which will be denoted by G hat. And this is by definition, I mean, for us, it will be by definition a discrete quantum group. And again, it will be defined in terms of some sister algebra denoted by C0 of G hat and the corresponding dual co-multiplication. And if you want a more precise picture, this sister algebra can be defined through the Peter-Weil theory as in the classical setting of compact groups by a C0 direct sums of matrix coefficients. This is an X. Okay. Besides these elementary definitions, we I would like also to recall a very small definition about quantum subgroups. So if G and H are two compact quantum groups, we say that H hat is a discrete quantum subgroup of G hat if the sister algebra defining H can be embedded into the sister algebra defining G in such a way that the co-multiplications are intertwined. Okay, and in this case, well, we'll write H hat inside G hat. And in case that the sister algebra of H is finite dimensional, we say that H hat is a finite discrete quantum subgroup. And this will be used at some point in the talk. Okay. So apart from this very brief recall, basically for the notations, let me start the talk by explaining the motivation and the context for our work. So the motivation is to define, or rather how to define a quantum Baum-Connes assembly map. So assembly map defining a quantum version somehow of the Baum-Connes conjecture. And the context is, of course, the Mayer-Nest approach to the Baum-Connes conjecture, which means in particular triangulated categories and the corresponding homological algebra on those categories. So first, let me start with this notion of compact objects. So given a category, so for us, we can just think about triangulated categories, but of course this definition can be given in a more general framework. A compact object in a category is an object such that the functor of homomorphism, viewed as a functor on the second variable, commutes with all countable direct sums. So this notion tries to encode somehow what are the finite or the small objects in the category. So for example, if the category is just the category of sets, the compact objects are precisely the finite sets. In the category of vector spaces, the compact object will be the finite dimensional spaces. And in the Kasparov category, which is actually in the example we are interested in, so this KK, Kasparov category, for example, the finite dimensional sister algebra will be compact objects. But if we want to go further, to give more, somehow in more interesting examples, we have already to use the UCT theorem. So using actually the QNet formula by Rosenberg and Schocket, then an A is a sister algebra in the UCT class, and the K theory of A is finite generated. Then, as a consequence of the QNet formula, we get that these kind of sister algebras are actually compact objects in the sense of the previous definition in the Kasparov category. Okay, so we'll see that already in this case it's not so easy to find such an example, because in the sense that we need this machinery of the UCT. But still, we want to know, or at least we want to understand what kind of objects are also compact in an equivariant Kasparov category. So with respect to a compact quantum group or a compact group, for us, we are interested in the compact quantum group case. So for this, we have a small remark, which is the Green-Yulk isomorphism gels already some kind a class of compact objects in an equivariant Kasparov category, because if A is, for example, if A is a finite dimensional sister algebra, and G is a compact quantum group acting trivially on A, then this is the C-star algebra with this trivial action is a compact object in the equivariant Kasparov category. And this is just a consequence of the Green-Yug. So we have here the trivial action, and then doing the descent homomorphism, we get an isomorphism between these two KK groups. And just we have to recall that the cross product is a functor, can be viewed as a functor which is compatible with countable direct sum. So we get what we wanted. So now the question is, what happens if G is acting non-trivially in the C-star algebra? And well, if A is somehow general, it could be very difficult to answer this question in sense of trying to defining compact objects in this general setting. But one of the main theorems in our paper with Kenny and Richard is that if A is finite dimensional and simple with an action of a compact quantum group, then we obtain a compact object in the Kasparov in the equivariant Kasparov category. So now we have, of course, two natural questions. The first is why these C-star algebras, and what is this useful for? Okay, so for the first question, so this kind of C-star algebras is related to the torsion for a discrete quantum group, okay, that I will define later on. And why this is useful is because this is related with the Meyer-Nest machinery to define the assembly map. So let me explain better these ideas. So first of all, the notion of torsion. An action of a compact quantum group is called torsion if the C-star algebra is finite dimensional and the action is ergodic. So I remember that in the setting of quantum groups, an action is rather a coaction of the C-star algebra defining G. So it will be some star homomorphism compatible with the multiplication of this form. And we can define, of course, the subalgebra of fixed points. And we'll say that the action is ergodic if there is only, the only fixed points are the scalars. So we can consider all these torsions action of G together. And that will be denoted by this tor of G hat. And then we give the following definition. We say that a discrete quantum group is torsion free if all torsion actions of G are the trivial one, or I mean, all are trivial up to Morita equivalence. Okay, so this is the definition in the sense of Meyer-Nest, and it's important to remark here that the notion of torsion or of torsion freeness is something related to the discrete quantum group, but it is actually a property of the compact. Okay, so maybe this will be more clear later when I try to justify this. I mean, to motivate this definition in terms of the torsion of a classical discrete group. But before that, so given this notion of torsion, we can already distinguish two kinds of torsion actions depending on the nature of the C-star algebra. So if the C-star algebra is, so remember, is finite dimensional, if it is non-simple, then we'll say that the torsion action is of permutation type. And if it is simple, we'll say that it is of projective type. An example of permutation type torsion action is just the canonical action of the quantum permutation group on Cn, when we see the quantum permutation group as the quantum automorphism group of the finite set of n elements. Okay, and a typical example, prototype example of projective type torsion is is, for instance, if we take the rotation group SO3 and we consider the projective representation of SO3 on C2, then we get a projective torsion action in the sense that I defined before, and we can do also the same thing for the Q deformation of SU3. Okay, so now let me explain somehow the motivation of what is the relation with the classical torsion of a discrete group. So we fix some discrete group gamma. The torsion of gamma is simply the collection of all finite subgroups of gamma. Okay, so if I consider some finite subgroup of gamma, and we translate this in terms of quantum groups, I'm just saying that lambda hat is a discrete quantum, is a finite quantum subgroup of lambda hat, of gamma hat. Sorry. So remember that the quantum group gamma is just given by the reduced sister algebra of gamma. So the same with lambda. Okay, and here I'm just saying that, well, if lambda is a subgroup of gamma, then we have also an inclusion of the reduced sister algebras. And this inclusion, of course, will be compatible with the K multiplications. So in this, using this inclusion, we can just extend the K multiplication defining lambda to this lambda tilde, and this can be viewed as an action, and actually a torsion action of gamma as a compact quantum group on this sister algebra. And so viewing the sister algebra of lambda equipped with this extension, it will be denoted by induced from lambda to gamma. But in principle, there is nothing to do with inductions. I mean, in principle, it's just a notation to remember that it's the same sister algebra but with an extension of the K multiplication. In any case, what we get is that from a torsion in the classical sense, we get a torsion in the quantum sense. And now the question is, do we get all torsions of gamma as a compact quantum group from these finite subgroups? Yeah.
Yeah. Could you go back to the previous slide?
Yeah.
What is the meaning of the identity, the second identity in the line where you define the torsion of gamma?
Is this a slide? This identity here?
No, in the previous display.
Oh.
No, not in the previous slide. The previous slide on the same.
Oh, here, yeah, okay.
And you define the torsion of gamma,
yeah.
right?
Equality.
Yeah, the equality. First, you define it as a set of elements.
Yeah.
To say it's a set of subgroups.
Yeah. Well, yeah. Yeah, maybe this is not very correct. But what I'm saying is that, yeah, given a finite ordered element, we consider just the subgroup generated by such an element, and then we get a finite subgroup, and in the other way around.
But you are considering only the cyclic subgroups?
No. No, I'm not considering only the cyclic subgroup.
Finite. You can have an infinite group generated by two elements of finite order.
Yeah.
It's the free group 2 with CMOD 2.
This is true. Yeah, maybe this is not very clear, but I mean, this is not very correct. This equality as I wrote it. Yeah, but what I mean, yeah, is just I want to consider this part of the equality. So yes.
So all finite subgroups, not just the cyclic.
Exactly. Yeah, exactly. Yeah, but you are right. Yeah, thank you for that.
So you cannot generalize the notion of sub element, but it's okay for finite subgroup.
Yes.
That's the point.
Yeah. yeah, so once we have this relation, we wonder if we can get all this quantum torsion somehow from the classical torsion, and the answer is almost, in the sense of this proposition, because we have to get we have to care about the projective representation of the finite subgroups. So more precisely, any torsion action of gamma as a quantum group is of the form the twisted system algebra of a finite subgroup with respect to some 2 cosine. This is basically what we have to retain here. So yeah, it's more than, in the quantum world, the torsion is more than only the finite subgroups, and this will be important when we want to generalize this for any quantum group. And yeah, before going on, just a remark is that the same game we played before, we can do it in general for compact quantum groups. So if I get a finite discrete quantum subgroup H hat of G hat, then again I can just extend the co-multiplication. I get some torsion action of G out of a finite discrete quantum subgroup. And the same thing more generally can be done for a torsion action of H hat. Then I can just extend this action to get a torsion action of G. But the point is that in this general setting, not all torsion actions of G are related to discrete quantum subgroups, finite or not. And the example is Sm plus. So Sm plus, we have seen that Sm plus is acting on Cn, and this is a torsion action, a non-trivial torsion action. Non-trivial torsion action. But also it is known that the dual of Sm plus does not have non-trivial subgroups, quantum subgroups. Okay. So the torsion in the quantum sense can be completely unrelated to the discrete quantum subgroups, and this makes some problems when we want to go when we want to go to some kind of definition of the assembly map, because, well, the first thing is that as in the usual setting, we cannot use the induction restriction approach anymore. And I mean, to explain this better, let me just recall some constructions in the classical setting. So let gamma be a discrete group. So in this case, we consider the corresponding Kasparov category, equivariant Kasparov category. And from gamma, we consider the family of all finite subgroups as before. Okay. And we pick one of these finite subgroups and consider the corresponding equivariant Kasparov category. Okay. Then we can do one thing, which is restriction from kk gamma to kk lambda. And we can also go in the other way around. We can do induction from kk lambda to kk gamma. And then in the major nest approach, there are two important facts or technical properties, which are, well, the restriction and the induction are adjoint functors. And the other point is that this family of finite subgroups, so this family of torsion, allows to define a nice subcategory in kk gamma, given by the induced sister algebras from lambda sister algebras. So lambda is a finite subgroup. And from this subcategory, they can define a convenient family of compact objects, in KK gamma. And well, these are the main points that Meyer and Nest use to define the assembly map and the Dirac element. So something similar, we want to do something similar in the quantum setting, but the first point, the first problem is that we cannot use this restriction and induction anymore, because now the collection of torsion is not subgroups, so of the discrete quantum group. So we cannot go from one category to a different one associated to a torsion object. And actually, the torsion elements are objects in the same category we started with. So if we want to do something similar, maybe we could, at the first stage, think about tensor product with this torsion object. But the point is that in the equivariant Kasparov category, with respect to a compact quantum group, there is no tensor product neither, because we cannot define this dual action for quantum groups. So there are a lot of technical problems that we have to deal with. And for this, one way to solve this is to introduce this fancy cross product that we call two-sided cross product for each torsion action. So let's fix some torsion action T. Okay, so here I will assume that T, I mean, this delta will be an action of G on the right, on the left, sorry. So it will be something like this, a map from T to C of G tensor T. Okay, so in this case, we can do the cross product by G, right? And then assume that we have another C-star algebra with an action of G, but now G is acting on the right. So it will be some map from B to B tensor C of G. And then we can also do the cross product respect to beta. And now the idea is that we want to perform some C-star algebra which encode both cross product at the same time. So if you want to see this as an algebra of operators, it will be something inside B tensor L2 of G tensor A. Sorry, A is T here. And well, this is what I said. As a C-star algebra, it will be generated by a copy of the dual of G, so C0 of G hat. And here we have three legs, so it will be something like this. And then on the right, we'll have a copy of T through a copy of T through the action delta. So here it will be something like this. And on the left, we have a copy of B through the action beta. And here it will be something like this, I think, if I'm correct. Okay. And then there is something more to take care is, so here, when we see B and T copies inside this C-star algebra, we have to take care of the copies of C of G represented in this L2 of G. And to this construction to work well, then with the computations, etc., when we want, for example, one of the copies of C of G, say this one, represented on L2 of G through the left regular representation, for example, and the other one here for T with the right regular representation. And then we will get two copies of C of G in the same L2 of G commuting each other. And this is the definition of this style. And the point is that this construction will give you a functor from kkg to kk, okay, for a given torsion action, which will be some kind of twisted descent map, or yeah, twisted descent map. And then we can define an adjoint of this functor, which will be associating to each trivial sister algebra just the tensor product with the torsion action T we are fixed from the beginning. And these two the main point with these two functors is to show that we get somehow a twisted Green-Julg isomorphism. Okay, and then and this for each torsion action, and then with same analogous argument as as I showed in the beginning, this will tell you that these torsion objects are compact in kkg. But well, here there is a small technical thing, is that we do all this when T is simple for the moment. Because, well, the point is that when T is simple, this will be, remember, a projective torsion of the compact quantum group. And the observation is that this projective torsion is actually related to the projective representation theory of the compact quantum group, the same way in that it happens for classical compact groups. And so you can imagine there will be some cocycle involved in the story, and this will allow to consider the formation of the quantum group, and then play a little bit with the formation, I mean, twisting and twisting to get this twisted version of the Green-Julg isomorphism. And once we have this, then the idea to define the assembly map is just, okay, assemble all torsion, and then define the assembly map by assembling all this torsion using the machinery of Meyer-Ernst. So this is basically the main idea. And if you have any questions now, and I think it's a good point to stop. I mean, to put questions. If not, then I will start.
Trivial thing.
Yeah.
Just a trivial question. When you define the torsion actions,
yeah.
You said you talked about non-trivial torsion actions.
Yeah.
Now, the thing that comes to mind when you say trivial action is not, I mean, that I imagine is mapping A to one tensor A.
Yes.
And but you also asked the action be ergodic. So the only one would be the complex numbers itself. Is that correct, or did I misunderstand?
This is completely correct. But I'm saying, when I say trivial, this maybe I didn't say, but it will be trivial up to Morita equivalence. So the action you are talking about is, of course, a trivial one, but also any action on a Hilbert space given by a representation of G will be also a trivial representation, a trivial torsion action. Because, yeah, anything which is Morita equivalent to C will be a trivial action. So, for example,
yeah, sorry.
Yeah. So if, for example, U is a representation of G, this will be also a trivial. I mean, all trivial action will be of this form.
Okay, and something else in your main theorem. you establish that the simple simple sister algebras,
Yes.
finite dimensional simple sister algebras are compact. No matter what action they have. Now, these are matrix algebras.
Yes, sure. Yeah.
I suppose that if you add two of them and consider the sum of the actions, that will be compact too.
Sure, but the point is that yeah, this is okay. But if we remove a simple and we get sister algebra, which is a sum of two matrices, then the action might not be just the sum of two actions. I mean, it can be.
Of course. So the problem is yeah. The problem is this, that the action need not be the sum, and then this may give non-compact things.
Well, it might be the case that they are not compact, but actually it's a work in progress. We are doing also this for any t, even when it is not simple. So in the end, this is true also, that all finite dimensional sister algebras and action of compact quantum groups are compact. Yeah, but this is not included in this paper. In this paper, we only focus on the simple case, but we are working on the general case.
Okay. Okay.
Yeah.
Thank you.
Okay. Yeah, and yeah, one reason we focus on this is because actually, I mean, when I define a torsion of projective type, the example or the prototypical example is the one given by the projective representation of a compact group. And the question is natural, is a relation also between this projective torsion that we call projective torsion and projective representations. And for this, we focus on the simple case, because again, we'll be able to make kind of twisting and untwisting strategies. And this is what I will try to explain now. So let me recall elementary notions for classical groups. So if G is a classical compact group, a projective representation of G on a Hilbert space H is just an action of G on the compact operators of H, right? A twisted representation, so given two cycle on G that will be measurable for the rest of the talk, our cocycles will be measurable. A omega representation of G on a Hilbert space, or rather a unitary twisted representation of G on a Hilbert space H, is a map from G to the unitaries of the Hilbert space, which is not a group homomorphism, but it is a group homomorphism up to these two cocycles. Okay, so these are just elementary notions, and this is also well known that there is a one-to-one correspondence between projective representations of G and twisted representations of G. So, for example, if we are given the two cocycle, then the alpha will be defined just by conjugating with this twisted representation. And in the other way around, we have just to show that the automorphism of the compact can be identified to the unitaries of the Hilbert space up to a constant of modulo 1. Okay, so now the question is, can we do the same thing for quantum groups? So for this, we need to include some kind of vocabulary. So first, what is a projective representation of G? In this case, we have to distinguish measurable and continuous, and it will be an action of G. So a measurable projective representation will be an action of G on the operators of the Hilbert space. So a measurable action, so will be a morphism of this form, and a continuous one will be a continuous action of G on the compact of H. So it will be a star homomorphism of this form. And of course, if we have a continuous action, I mean, a continuous projective representation, we'll get a measurable one because we can just extend to the multipliers. But it turns out that here in the quantum world, the measurable projective representations will not be the same as the continuous one. And this will be related to some technical property about the cocycle, which will be the regularity of the two cocycle, or of the twisted quantum group.
One small question: the bar on top of the tensor.
Yeah.
What?
This means just is the tensor product as von Neumann algebras. So yeah, when I write here the tensor product without any decoration is just the minimal tensor product, and this will be for von Neumann algebra. Yeah, so this a remark to do because so here I didn't say it, I think, but here I'm assuming G to be second countable, and our Hilbert spaces are separable. So here the projective representations for a compact group will be always continuous with these topological assumptions. But it turns out that for quantum groups we have to be more careful. In any case, let's stick with the measurable setting. So given now, so what is a two cocycle for a quantum group? It will be some unitary element of this von Neumann algebra satisfying this equation here. And this equation here is just a dual version of the two cocycle condition. Okay. So given the two cocycle condition, just dualize this in the usual way, and we get this condition here. And with such a two cocycle, we can define a twisted co-multiplication, which will be a linear map, delta omega, from L infinity to G to L infinity to G tensor L infinity to G, which is just the co-multiplication, but multiplied on the left by the two cocycle. So this recalls or reminds some of the properties of the co-multiplication itself. For example, this fourth property here is this density property reminds the cancellation property of the co-multiplication. Or for example, the third property here is like the co-associativity for this twisted co-multiplication. But it's important to remark that this delta omega is a linear map, and it is not, for example, a map of algebras, because we'll have this first property here. It's not an algebra map, or we have also this relation with the star. So here the L infinity of G must be thought instead of being an algebra, is like an L infinity comodule or module. So this delta omega will be rather kind of comodule map. In any case, we have all these properties which are good enough to develop the projective representation theory. And well, with all these preliminaries, this vocabulary, we can already define what is a twisted representation with respect to a two cocycle. And this will be a unitary, so like a representation, okay? But now, and then with this condition, instead of demanding the representation condition with respect to the co-multiplication, we have to include here the twisted co-multiplication. So if you want, the right-hand side of this condition is the analogous to what I wrote before, like pi x, pi y, okay? And here, the left-hand side is the analogous part to what I wrote before, like omega xy times pi x times y. Okay. So this is just the dual version of the previous definition of twisted representation. So the question is there a one-to-one correspondence between projective representations of G and twisted representations of G? And before answering this, I have to explain some of the already results about this theory. And the point is that actually all this projective representation was already formalized by Kenny de Kommer in 2012 with the notion of Galois co-object. And this is kind of generalized to co-cycle. Okay, actually, what I have introduced right before, so this twisted representation, twisted co-multiplication with L infinity of G and well, L2 of G is actually an example of Galois co-object. So I don't need the precise definition, but it's just a triple, well, where L2 of D, L2 of N will be some Hilbert space. So in our case, it's just L2 of G, N will be some closed subspace of operators in operators between, I think it was, if I remember correctly, from L2 of G to L2 of N. And delta N will be some linear map, as before, from N to N times tensor N, satisfying properties analogous to the twisted co-multiplication. Okay. And in this general framework, Kenny already showed that there is a one-to-one correspondence between projective representations and Galois co-objects. But I wanted something more precise. I wanted, because I didn't say that, this is developed for all locally compact quantum groups. Okay. So I wanted something more precise in the compact case. So I wanted that all these Galois co-objects should be of the form the twisted co-multiplication with respect to some two cosine. And actually this has a name. So the Galois co-objects which are of this form are called cleft. And there was an open question if whether the Galois co-object associated to a compact quantum groups are always cleft. And already in the paper of Kenny, there was some work in this respect. So if G is G is commutative, of course, its Galois co-object will be cleft. This is basically because it boils down to the classical case of compact groups. But also it happens for co-commutative case. So if G is of the form the C-star algebra of a discrete group. In this case, also all Galois co-objects are cleft, and this is basically contained in. So let me go back to this proposition here. So here, remember, I said that all torsion actions of gamma as a compact quantum group are twisted C-star algebras of finite subgroups. So basically what Kenny observed is that actually when the compact quantum groups is co-commutative, all Galois co-objects are of this form. And this gives you the cleftness property. Okay. So now the question is, what happens in general? For any compact quantum group. So before that, we can give a very nice observation. So assume that delta is a measurable projective representation of G. Okay, and assume that this delta is already unitary implemented, which means that it's just conjugation by some unitary. Okay, then what I'm saying is that in that case, the unitary implementing the action, the projective representation, is already a projective representation with respect to some two cocycle. And this is not very hard to see because, well, we have just to do some computations. If delta is implemented by this unitary, we can compute delta of A, and then again delta, we apply delta in the first leg, and we develop this, we expand this with this formula here, with this implementation. And on the other hand, instead of applying the action in the first leg, we can apply the multiplication in the second leg. And again, we expand. And we compare these two. And the point is that since delta is a coaction, these are the same, because delta is an action of G. So this is just the compatibility with the multiplication. And comparing this yields the existence of some unitary. And then, well, some more computations, I mean, some further computations will give you that this unitary will be already a two cocycle, and by construction, the unitary implementing this action will be actually a projective, a twisted representation. Okay, so in the end, thanks to this observation, our question turns out to be: is every projective representation of G unitarily implemented? So it's enough to show that it is unitarily implemented. So one very easy case, but very illuminating, is the finite dimensional case. So if G is a compact quantum group and we get a finite dimensional projective representation, then it is unitarily implemented. And this is the reason for this is basically this lemma here, which is also an elementary one. So assume that in a von Neumann algebra M, we have two matrix unit systems defining two copies of K by K matrices inside M. Then I'm saying that then there exists a unitary in the von Neumann algebra intertwining the two matrix units. And the reason for this is basically, for example, take the projection 1, 1, E11, and take the projection F11. These are two projections with the same central support, and they sum up to 1 in the K0 group of M, right? So then we deduce that E11 is actually Murray von Neumann equivalent to F11. And then with the corresponding partial isometry, we construct the unitary U. And then once we have this lemma, then the theorem follows quite easily, because, well, we have a projective representation of G. We assume that our H is finite dimensional. We fix some basis. We consider the corresponding matrix units, and then we consider the image of these matrix units by the action, and we consider these other matrix units. Then we are in the assumption, in the context, in the framework of the lemma, and then we apply the lemma. And the point is, the idea is to generalize this lemma or this argument in the infinite dimensional case. But before that, we already obtained the following corollary: is that if G is of CATS type, so a compact quantum group of CATS type means that the Haar state is tracial. So in this case, then every projective representation is cleft. So in this case, using the finite dimensional case, we already answer the general question for the CATS type quantum groups. And well, I won't be very precise here, but if you think about these projective representations, like in the context of twisted representations with respect to these Galois co-objects, then you can develop also, I mean, Kenny developed this theory of this representation theory. So in particular, you have this Peter Weil and the composition into irreducibles, etc. And it turns out that in the CATS type, all the irreducible representations, rather the projective representations, are finite dimensional. And so assuming without loss of generality that our projective representation is irreducible, then we have just to apply the previous theorem together with the result of K. And for the general case, well, I think I'm running out of time, but for the general case, when G is not of CATS type, the idea is that we want to reduce to the CATS type. And well, for this, we have just to remark, and this is a well-known theorem. When I say this is a folklore, it's because I'm not very sure to whom I have to associate this theorem, because I think it already appears in some work of Baez, but also in Soltan's paper. So I'm not sure who wrote this in the first time. But in any case, the idea is that the von Neumann algebra of a compact quantum group can be divided or split it into two parts. A part which is of CATS type, I mean, a part which will define a quantum subgroup of CATS type. And so remember, I said that CATS type means that the hard state is threshold. So necessarily the part of CATS type inside L infinity of G must be a finite von Neumann algebra. So the idea is, okay, we consider all the finite part of the von Neumann algebra and we pull out all the infinite part. So this will be a properly infinite part of the von Neumann algebra of L infinity of G. And then, well, using this decomposition, we try to generalize the argument of the finite dimensional case for the infinite dimensional case, taking a minimal projection E of our B of H, and then try to show that these two projections are again unitary equivalent in this von Neumann algebra, showing that they are unitary equivalent in each part of L infinity of G. And yeah, I think I have already said everything with everything. Thank you very much.
Any questions? I have a small question. When you told us about this twisted green yolk.
Yes.
So you said that to define the assembly map, one puts all of these together.
Yeah.
Could you give some hint of an idea of?
Yeah.
I mean, I want you to give another talk. Just a simple idea.
Yeah, let me, maybe I can, yeah. Yeah, I mean, this is basically, it's nothing new. In the last part is just apply the Mayer-Nest strategy. So Mayer-Nest consider this induction and restriction, and to define the assembly map, they put together all these inductions and restrictions functor to get another adjunction between bigger functors. And this is the same. So here we have Oh. I'm sorry, it doesn't work. So we have this functor here for each torsion action, okay? And then what I want is to consider the functor f, which will be basically the product of all these functors, which will go to the product of all these categories, and then define the adjoint in the same way. I mean, the adjoint will be just the sum. So remember that what we showed is that this is adjoint to this other functor here. I don't remember how I tau t. So here would be the direct sum of all the tau t's. And then I apply just the Meyer-Ernst machinery. These two functors will be adjoint. And basically, I'm saying that the projective objects in KKG will be the image of this. This will be the projective objects. And then we apply just the general theorems from their homological algebra that they developed.
Okay, I see now what you meant.
Yeah.
Thank you. Are there any further questions? Okay, so we thank Rubén again.
Thank you.
And we can